What are gradient factors?
Gradient factors? That's it. We have all encountered this incomprehensible graph, yet it's supposed to help us understand the concept. This representation is very useful for clearing up any confusion on the subject, but we must admit that it is not very easy to interpret. Let's start by simplifying. The 16 compartments published by Bühlmann are all represented here, but we will keep just one. We will even, for the moment, focus on a two-dimensional space to represent the M values. On the x-axis, we find the ambient pressure. On the y-axis, the tolerated inert gas pressure is represented. For air diving, this is the maximum nitrogen tension that the compartment can handle. In other words, the M value. The median of these two axes, often referred to as the ambient pressure line, connects the point where the nitrogen tension is equal to the ambient pressure. To the right of this line, the ambient pressure is greater than the nitrogen tension, and to the left it's the opposite. But this line has no real importance. When the scales of this graph are expressed in the imperial system in feet of seawater, the zero ambient pressure corresponds to the atmospheric pressure at sea level. The M values allowed at the surface are located on the vertical axis. This is why Workman designated them as M0, as they are the maximum values at 0 meter. Bühlmann used scales in bars, allowing the representation of pressures below atmospheric pressure at sea level, and thus describing altitude-related phenomena. This time, the M values at the surface are no longer represented on the vertical axis, but on a line corresponding to an ambient pressure of 1 bar. Let's not make things more complicated than they are, and focus on just one compartment. If you stay at the surface long enough, the nitrogen tension in the various tissues of your body will reach equilibrium. For the compartment we are interested in, but it will be the same for others, the nitrogen tension it contains is equal to the inspired nitrogen pressure. Still keeping it simple, let's assume that this inspired nitrogen pressure at the surface is equal to 0.8 bar, and represent it as an arrow with a height of exactly 0.8 bar. If you go up in altitude, the ambient pressure decreases. Depending on its period, the nitrogen tension in our compartment will also decrease, but more slowly. The compartment desaturates. Let's return to sea level and go diving. We descend onto a famous wreck in the south of France. On the deck, the ambient pressure is 5 bar. We are breathing air, so the inspired nitrogen pressure is 4 bars. The compartment we choose to follow becomes saturated, neglecting gas exchanges during the descent. The difference between the nitrogen tension it already contains and the inspired nitrogen partial pressure is 3.2 bars. This difference is often called the pressure gradient. This compartment has an 8-minute period. After this 8 minutes spent exploring the wreck, our compartment has absorbed half of the pressure gradient. It therefore contains 2.4 bars of nitrogen. If we were to return to the surface at this moment, the nitrogen tension in our compartment would still be lower than its M value at atmospheric pressure. We could reach the surface without mandatory decompression. If we stay a little longer on this beautiful wreck, after another 8 minutes, it has again absorbed half of the remaining gradient. The nitrogen tension in the compartment reaches 3.2 bars. Ascent directly to the surface is no longer possible. A first stop at a depth of 6 meters will allow our compartment to eliminate enough nitrogen for us to proceed to the next stop. We will then have to wait for 5 minutes at 3 meters before we can return to the surface.
This is not the GF, it's the M values.
You are absolutely right, but you will agree that these explanations weren't useless. Let's go to the heart of the matter. A gradient factor is nothing more than a mathematical trick used to reduce the tolerated nitrogen tension in the compartments. Let's go back to our favorite compartment and apply a GF of 0.8. Here is the new M-value line. Now let's go back to the same dive as earlier. You remember that we could go directly to the surface after exploring our favorite rake for 8 minutes. This time it's impossible. The saturation level of our compartment exceeds the tolerated nitrogen tension. We will have to stop at 3 meters. With a 60% GF, we would have been forced to stop at 6 meters. This trick allows for an additional safety margin compared to the original algorithm. This adjustment option has been named and renamed several times over the years. Reduction factor, or more recently conservatism. But even if the methods differ, the result remains the same. Divers using helium to reach depths unreachable with air need to slow their ascent earlier to allow the slide guys to be eliminated safely. Deep divers are used to making a first stop at a significant depth. They could achieve this result by applying a 0.3 or 0.4 GF, but that would mean unnecessarily lengthening the shallow stops. To avoid this, Eric Baker suggests using two different GFs, GF low and GF high. The practice is to indicate the GF pair in the order low-high, for example 30-70. The method involves applying the GF low to the M-value for the first stop and the GF high for the surface M-value. Let's see what this implies. Let's return to our M-value lines for our usual compartment, without a GF and with GFs of 80-80. Let's take a GF low of 30. Baker proposes a formula to calculate, based on our current nitrogen tension, the decompression ceiling that will be imposed by this GF low. For the compartment we are interested in, a first stop will need to be made at a depth of 15 meters. Let's set a GF high at 70. This time we need to calculate the nitrogen tension we will accept once we reach the surface. The same formula still applies, but in the opposite direction. We now have 2 points, each defined by a nitrogen tension and a pressure. The simplest method for determining the GFs for intermediate stops is to draw a line between these 2 points. Here are the M values obtained for a GF setting of 30-70. Let's return to the brake's deck as we begin our ascent. As planned, our first stop at 15 meters lasts for 1 minute. This allows our compartment to eliminate enough nitrogen for us to reach the second decompression stop without exceeding the M value. We then stay for 3 minutes at 12 meters, then 4 minutes at 9 meters, 5 minutes at 6 meters, and finally 11 minutes at 3 meters, before heading to the surface. Such a setting is often used in mixed gas dives. It is not recommended for air dives, as such a deep stop could increase the risk of decompression sickness. A setting based on twin GFs is preferable, as it helps avoid a deep stop while maintaining a certain safety margin. But if two divers use very different settings, one will impose an endless decompression time to the other, and especially deep stops. If you are waiting for these divers at the surface, don't be surprised if they are still under the SMB while the others are already back.